Okay, good afternoon, all of you. Welcome to this lecture of refrigeration and air conditioning. So, today we are going to finish the numericals of VCR cycle, vapor compression refrigeration cycle. Then we'll see what are the parameters that affect the vapor compression cycle. Okay, so before I go ahead, I see a lot of students who are very irregular. They are present today. So for them, I will repeat this thing once again. Uh, Okay, so I'll first take a quick recap of what we have learned in last lecture. Then I will take the example. Okay, so we are in VCC, that is vapor compression cycle. Also, we call it as VCR cycle, vapor compression refrigeration cycle. Okay, so what you see on the screen, many of you already know it. So that is a pH chart, pressure versus enthalpy. So on y-axis we have pressure. So but so what you see on the screen, that is a pH chart. So on y-axis we have pressure, and on x-axis we have enthalpy. So that enthalpy is specific enthalpy. Then what you see here, this curve that we call it as saturated liquid curve. What you see on the right, so that is what we call it as a saturated vapor curve. Okay, so they both meet at one point. So that point we call it as a critical point. Okay, and so in VCC cycle or VCR cycle, we have two constant pressure processes, and one we have isentropic process and one is isenthalpic process. So if I give the marking here, so suppose this is 1, 2, 3, and 4. So point 1 is the end of evaporator, okay, or we can say it is the starting of the compressor. Then 1 to 2 is a isentropic compression process, so that entropy remains constant. Then 2 is the end of compression. Then from 2, that refrigerant, that high pressure, high temperature vapor will enter the condenser. So 2 to 3 is a constant vapor heat rejection process. So you see there are two pressures we are dealing with. The lower is what we call it as a evaporator pressure, and the higher one we are calling it as a condenser pressure. Okay. Now, so at 3, that heat is rejected and that vapor is converted into liquid. Okay, so why it is liquid? Because it is lying on saturated liquid curve here, so that is why it is a liquid. So from 3 to 4, it will pass through expansion wall where the constant enthalpy expansion will take place. Then at the 4, we have low temperature, low pressure, liquid plus vapor refrigerant, and that will pass through the evaporator. Why it is a liquid plus vapor refrigerant? Because it is lying in between saturated liquid curve and saturated vapor curve. Okay, so this side on the left of saturated liquid curve we have subcooled liquid. On the right of saturated vapor curve we have superheated vapor. So whatever in between, that is nothing but liquid vapor mixture. Okay. So Prasad is here. Prasad Magi. So I'm taking the revision for your kind information. So today we have Pratik also, Pratik Mandwale. I don't know where he was lost. Pratik? Pratik Mandwale?
Yes, sir.
Are you there?
Yes, sir.
Where were you?
Sir, at work.
At work.
Yes, sir.
Okay, okay. I thought you did some time travel.
No, sir, no.
You went in 2030 and you still found out that the Corona is still there. Huh?
No, sir. No, sir.
Then you return back to 2020.
No, sir.
Okay, okay. So be regular henceforth.
Yes, sir.
Okay. Okay. So this is the VCC on pH chart. Then we give some notations, symbols also. So from this onwards, we saw some examples of it. So we have different processes: dry saturated vapor after compression, superheated vapor after compression, superheated vapor before compression, undercooling and subcooling of refrigerant. Then I showed you what are the symbols we are using while solving the numericals. So if you take enthalpy on the saturated vapor curve, so that we calling it as a HF. Okay, so that is nothing but enthalpy of liquid. If you take enthalpy on a saturated vapor curve, so that we are calling it as a HG. That means enthalpy of gas. If you take enthalpy on the superheated region, so I have taken here HV. So here that formula I have given, HV will be enthalpy of gas, that is a vapor, plus some quantity, that quantity is Cp delta T. If you take enthalpy on the subcooled region here, so if I have taken the symbol as HL, so that HL, it will be what? It will be HF. Okay, so HF is nothing but enthalpy of saturated liquid minus some quantity, so minus Cp delta T. So these are the symbols generally used, HF, Hg, and if you take the difference between Hg and HF, so that will give you HFG. Okay, so if you remember this, you already have used in applied thermodynamics while solving the Rankine cycle examples. So similar symbols we are using in VCR cycle. Okay, so we solved two examples already. So first one was dry saturated vapor at the end of compression. Second was superheated vapor at the end of compression. So we had superheated vapor. Now third we'll take subcooling. Okay. So example is in front of you. So I advise you to be ready with notebook and pen, and write down the given data. Okay. So uh, you read the problem, and we'll write the given data. Okay. So what it says, a vapor compression refrigerator works between the pressures 4.93 bar and 1.86 bar. The vapor is superheated at the end of compression, its temperature being 25 degrees Celsius. The liquid is cooled to 9 degrees Celsius before throttling. The vapor is 95% dry before compression. Using the data given below, calculate the coefficient of performance and refrigerant effect per kg of working substance circulated. So the table is given in front of you. So quickly I will go through it. So what is given? There are two pressures. Higher pressure, as you know, that will be condenser pressure. Okay, so this will be condenser pressure, that is given as 9 bar. Then the temperature is given. So this temperature is nothing but saturation temperature. Okay, saturation temperature, that is given at 36 degrees Celsius. Now see in the problem, that temperature at the end of compression is being 25 degrees Celsius, and the liquid is cooled to 9 degrees Celsius. So see here, saturation temperature for 9 bar, it is 36 degrees Celsius, but the liquid is cooled to 9 degrees Celsius. That means there is a subcooling. Okay, जेव्हा जेव्हा तुमचं सॅच्युरेशन टेम्परेचरच्या खाली टेम्परेचर जातं त्यावेळेस काय असतं सबकुलिंग. ज्यावेळेस तुमचं टेम्परेचर सॅच्युरेशन टेम्परेचरच्या वर जातं त्यावेळेस काय असतं सुपर हिटिंग. सॅच्युरेशन टेम्परेचर म्हणजे काय, ज्या टेम्परेचरला फेज चेंज होते लिक्विड टू वेपर. ओके, देन दे गिव्हन एन्थाल्पी ऑफ सॅच्युरेटेड लिक्विड. सो लिक्विडची एन्थाल्पी आहे म्हणजे काय असणार आहे ते HF. Then they have enthalpy. Again, enthalpy is given, but they have given latent heat. Latent heat means that will be HFG. So that is nothing but HF, sorry, not HF, Hg minus HF. Now next is they have given the evaporator pressure here. So lower is evaporator pressure. So temperature, the saturation temperature is minus 7 degrees Celsius. Enthalpy is given again HF, and here HFG is given. Okay. So I think the table is repeated or what here. Okay. So next is given the specific heat at constant pressure for the superheated vapor is 0.645 kilojoule per kg Kelvin, and for liquid it is 0.963 kilojoule per kg Kelvin. So this is your problem. First you draw the pH and TS diagrams. On that diagram we will show the given values. Okay. So just wait, I will quickly correct these values. See, these values are something incorrect. So first we have here condenser, that is a 4.93. Okay. So wait till I correct the values in the example. So the given values are same as our previous example. So that table has to be corrected. So let this, so where I'm drawing that pH and TS diagrams, temperature versus enthalpy. So first I will draw that pH chart. Okay. This is little bit awkward. Okay. So in this case, what they are given, so I will start from the beginning. So they are given two pressures. That is, first is 4.93 bar and second is 1.86 bar. So they are given the condenser pressure and evaporator pressure. Now what is they are saying? Vapor is superheated at the end of compression. So vapor is superheated at the end of compression and its temperature being 25 डिग्री सेल्सिअस. आता तुम्हाला काय चेक करायचं आहे, हे सुपरहिटेड आहे का नाही तुम्ही कसं चेक करणार? ठीक आहे, जरी त्यांनी दिलं असेल तर जर त्यांनी दिलंच असतं की हे सुपरहिटेड आहे का नाही, तर तुम्ही कसं ओळखलं असतं? तर तुम्ही चेक करायचं की कंडेन्सर प्रेशर, हायर प्रेशर कुठलं आहे 4.93, म्हणजे ह्या प्रेशरला सॅच्युरेशन टेम्परेचर किती आहे 14.45. ठीक आहे, आणि हे व्हॅल्यू जी आहे 25 डिग्री सेल्सिअस, it is greater than 14.45. That means this temperature is greater than saturation temperature. That means it is superheated. ठीक आहे, जरी तुम्हाला त्यांनी दिलं नसतं सुपरहिटेड आहे का नाही, तरी पण तुम्ही हे डिटरमाइन करू शकता. Now next they have given the liquid is cooled to 9 degrees Celsius before throttling. Okay. परत हे जे आहे liquid is subcooled. So liquid is cooled after the condenser. Subcooling takes place. So again that 9 degrees Celsius, if you see, it is less than 14.45. That means what is it? What it means? It is less than the saturation temperature. जेव्हा टेम्परेचर सॅच्युरेशन टेम्परेचर पेक्षा कमी असतं त्यावेळेस काय असतं सबकुलिंग. So easily by looking at the problem, even they don't mention superheated, subcooled, easily you can find out. Okay. Next is given vapor is 95% dry before compression. So I will start drawing my diagram from this data. So I will assume somewhere here. So 95% dry means it is a wet. So it has some liquid and it has 95% vapor. So let us this be our point 1. आता ह्यानंतर काय होणार आहे isentropic compression, and they have given that vapor is superheated. That means this point 2 will lie on right side of the saturated vapor curve. आता ह्यानंतर काय आहे, it will pass through the condenser. So constant pressure, heat rejection takes place. It will come to the point here. But this is not the end. Okay, so it is further cooled. Okay, so it is further cooled, so it will go to the subcooled region, and then this will be our point 3. So this will be point 3 dash. Now we have constant enthalpy expansion, so again this will follow this. So let this be 4. Okay, and then sorry, this is a isenthalpic process, so this will be a straight line. So this will be a straight line because it is an isenthalpic process 3 to 4, and then it will join to 1. So this will be 0.4. So 4 to 1 evaporation, 1 to 2 compression, 2 to 3 is a constant pressure heat rejection, 3 to 4 it is a expansion. So if I draw it on a TS diagram, how it will be? So here in this case, let's start from here. So that paper is okay, and compression will take place here. This is point 1, point 2. Why it is a straight line? Because it is an isentropic compression. That means that line will become straight because their entropy remains constant. S1 is equal to S2. So from 2, there will be cooling to saturation vapor curve. So this will be point 2 dash. Then there will be what? It will pass through the condenser. Okay. Then there is subcooling. So subcooling, it is shown on the same curve here. So this will be 0.3 dash, this will be 0.3. Because of subcooling, the temperature reduces. Okay. So this is your T saturation, and here, as it is subcooled, that temperature is lower. From this, that isenthalpic process is shown 0.4, and 4 to 1 is a evaporation. Okay. So as I said, drawing the diagram is also a most important thing. Now we'll solve the problem. So I hope you are drawn up to this point. Okay, so what is given in this case? It is enthalpy values. I will first write it down. So they have given this value of enthalpy HF here. Okay, here and here. So I will draw it. So for pressure 4.93, the enthalpy is given. So that means here in this case for this pressure, so this is a 4.93 pressure, that is a condenser pressure. Then next we have a evaporator pressure. So what they have given in this case, they have given this HF value. So this HF is given, how much they have given? 49.47. Next thing they have given latent heat, they have given 147.8. So that means they have given this value. Okay, so let us say this 0.2 dash. This value they have given. How much they have given? 147.8. Okay. Next thing, they have given for the pressure 1.86. So they are given the enthalpy of saturated liquid as 21.67. That means they have given here. So this may be point, let us say 4 dash. This enthalpy they have given. Okay, so this enthalpy they have given as 21.67, and they have given that this latent heat, that means HFC, they have given as 161.41. That means they have given this enthalpy value. So this enthalpy is given as 161.41. Okay. Now regarding temperatures, what they are given is for pressure of 4.93, saturation temperature is 14.43. Okay. So here in this case, this saturation temperature, here it is 14.43. Now that liquid is subcooled to how much temperature? 9 degrees Celsius. So it is subcooled to 9 degrees Celsius. Suppose this scale is degree Celsius. And the saturation temperature, superheated vapor temperature, they are given as 25 degrees Celsius. So this 0.2, which is a superheated vapor, so that will be at point. So that temperature, it will be 25 degree Celsius. Okay. So if you draw the horizontal line, this point will be 25 degrees Celsius. So I hope I have drawn all these things. So yes, again the point 1, it is a wet liquid, and at this point that X dryness fraction is equal to 0.95. 95% means that will be 0.95. The dryness fraction is given as 0.95. Okay. So given I have written all the data above, now our objective is to calculate COP. Okay. So what is the given in this case? They have given the pressure at 0.2, that will be pressure at 0.3 equal to 4.93 bar. Then we have P1 is equal to P4, which is equal to 1.86 bar. Then we have T2, temperature of superheated vapor as 25 degrees Celsius. So if I convert into Kelvin, so that will be plus 273. So that will be 298 Kelvin. Okay. Next thing, they have given T3. T3 is given 9 degrees Celsius plus 273. So that will be 282 Kelvin. X is given in this case, that is 0.95. And they have given CP of superheated vapor as 0.645. So that unit is kilojoule per kg Kelvin. And they have given the specific heat of liquid, that is 0.963 kilojoule per kg Kelvin. Okay. So this is the given data. Now after given data, so you follow this instructions step by step. If you go step by step, there won't be any confusion. तुम्ही जर पहिल्यांदा गिवन डेटा जर चांगल्या प्रकारे लिहून घेतला तर तुमच्या बऱ्याचशा आयडिया क्लिअर होतील की तुम्हाला काय करायचं आहे. So in this case, if I want to calculate the COP, okay, COP will be what? Refrigeration capacity QL divided by compressor work. So that will be a formula will remain, so that will be H1 minus H4 divided by H2 minus H1. आता ह्या केस मध्ये बघा की कोणतीच व्हॅल्यू तुम्हाला डायरेक्टली दिलेली नाहीये. जसं आपल्या प्रिव्हियस एक्झाम्पल मध्ये काय असायचं, कुठला तरी पॉइंट आपला सॅच्युरेटेड वेपर किंवा सॅच्युरेटेड लिक्विड लाईनवर असायचा, त्यामुळे आपण डायरेक्टली याची व्हॅल्यू काढू शकत असायचो फ्रॉम टेबल. But in this case, each value we have to calculate. Okay. So I'll begin with the H1. So first will be calculation of H1. Okay. So H1 is in liquid region. So H1 will be equal to HF1. Okay. So enthalpy of liquid at pressure of 1 plus dryness fraction into HFG1. ठीक आहे. तर आपल्याला HF1 दिलंय, that means enthalpy of liquid at pressure 1. So that is given in this case is nothing but 21.67 kilojoule per kg. ठीक आहे. तर हे मी कसं घेतलं लक्षात घ्या की आपण इथं घेतलं की HF1 म्हणजे काय, एन्थाल्पी ऑफ लिक्विड ऍट पॉईंट 1. तर 1 चा प्रेशर काय आहे 1.86. मग मी काय करणार, टेबल मध्ये जाणार 1.6 बघणार आणि एन्थाल्पी ऑफ सॅच्युरेटेड लिक्विड बघणार किती आहे 21.67. ठीक आहे. आता ह्या केस मध्ये HFG काय आहे, HFG1 इज नथिंग बट द लॅटेंट हीट. बरोबर. लॅटेंट हीट त्यांनी किती दिले या केस मध्ये, for the pressure of P1, that is 161.41. So that is 161.41 kilojoule per kg. So H1 will be equal to 21.67 plus 0.95 into 161.41. So please calculate this for me. So I have one answer. Others also please calculate and confirm your answer. So shall I call by name? Amol Lagne, please calculate. Amol Lagne. So there are two different answers. The difference is like 5 kg per kilojoule per kg. So which one is correct? So others also please calculate and confirm your answers. So Rohit, please calculate again. I think you are getting some higher value. So I will take Pratik's answer, or I will take Rohan's answer. So that will be 175.04 kilojoule per kg. Okay, so that was our first point, calculation of H1. Next will be calculation of H2. So calculation of H2. ओके. H2 ची व्हॅल्यू कशी काढायची, आपल्याला काय करायचं की ह्या पॉइंटची एन्थाल्पी काढायची. इथं आहे तुमचं H2 इज एन्थाल्पी ऍट पॉइंट 2. तर 2 पॉइंट कशामध्ये आहे, 2 पॉइंट तुमचा आहे सुपरहिटेड रिजन मध्ये. त्याची एन्थाल्पी कशी करणार, तर तुम्हाला पहिलं माहित पाहिजे एन्थाल्पी ऍट पॉइंट 2 डॅश प्लस CP डेल्टा T. ठीक आहे. So enthalpy of at point 2, H2 will be equal to H2 dash. So H2.2 dash point is here. 2 dash point lies on saturated vapor curve. So I will write this as Hg2 dash plus Cp delta T. Delta T will be what? T2 minus T2 dash. ठीक आहे. आता Hg2 म्हणजे काय आहे, तर एन्थाल्पी ऑफ गॅस. जर आपण टेबल बघितला तर या टेबलमध्ये कुठेच तुम्हाला एन्थाल्पी ऑफ सॅच्युरेटेड वेपर दिलेली नाहीये, पण त्यांनी तुम्हाला काय दिलंय, सॅच्युरेटेड लिक्विडची एन्थाल्पी दिली प्लस तुम्हाला लॅटेंट हीट दिले. इफ आय ऍड दीज टू थिंग्स ऑटोमॅटिकली आय विल गेट एन्थाल्पी ऑफ वेपर. ओके. So Hg, enthalpy of vapor at point 2 dash will be equal to enthalpy of saturated liquid at point 2 dash. Okay. प्लस दॅट HFG 2 डॅश. तर ही एन्थाल्पी दिली का. आता 2 डॅशचं प्रेशर काय आहे 4.93. तिथली एन्थाल्पी दिली का त्यांनी, दिली. सो दॅट इज अ 49.07. सो दॅट विल बी 49.07 प्लस HFG त्यांनी दिले का लॅटेंट हीट, तर त्यांनी दिले 147.8. ठीक आहे. So 147.8. So this will be 0.87. So 196.87. I hope this is correct. Okay. And T2 dash, you know, that is the saturation temperature. T2 dash is nothing but saturation temperature at that pressure 4.93. बार किती दिले त्यांनी सॅच्युरेशन टेम्परेचर 4.93 बारचं सॅच्युरेशन टेम्परेचर आहे 14.45 ठीक आहे 14.45 and temperature at 0.2 after compression that is also given in this case that is a 25 degrees Celsius or I will take 298 Kelvin and this will be as a Kelvin मध्ये केलं किती होईल plus 273 so that will be 287.45 Kelvin ठीक है so I will now calculate so that H2 will be equal to 196.87 प्लस सीपी आता सीपी कुठला घ्यायचा आपल्याला दोन सीपी दिले ठीक आहे तर ह्या केस मध्ये त्याने दिले बघा एन्थाल्पी ऑफ सुपरहिटेड वेपर इट इज 0.645 तर आपल्याला हा सीपी घ्यायचा आहे जर मी सब कुलिंग मध्ये गेलो तर मला लिक्विडची घ्यावं लागेल लिक्विडचं किती आहे 0.963 सो इन दिस केस वी हॅव टू टेक 0.645 so plus 0.645 into delta t तर delta t किती घेणार मी 298 minus 287.45 okay so can you calculate this for me So I have three answers in front of me. I will take Pradyumna's answer. So that H2 as he has calculated that is equal to 203.67 unit will be kilojoule per kilogram. Now third thing is calculate H4. So third thing is to calculate H4. So why I am calculating H4? So see the formula of COP. We need these values. So out of these values, we have calculated H1, we have calculated H2. Now the remaining part is H4. So first I will calculate that. Now I will calculate the calculation of, I will calculate H4. So that will be calculation of H4. So see here, H4, how to calculate H4. So how we are calculate up to this point. So this is the, if you see the diagram here. So here it is your point H4. Okay. And 3 to 4 it is a isenthalpic process, that means the enthalpy remains constant, so enthalpy at 0.4 will be equal to enthalpy at 0.3. okay so H4 is equal to H3. Now how to calculate H3? Now see 0.3 it lies on subcooled region, so it will be what enthalpy at 0.3 dash minus Cp delta T. okay So how to calculate H3? H3 will be equal to enthalpy at 0.3 dash. Now 3 dash point lies on saturated liquid curve. त्यामुळे मी काय लिहिणार आता इथं HF3 dash minus Cp delta T. Delta T काय असणार आहे ह्या केसमध्ये T3 dash minus T3. का बरं असं घेतलं मी? Because it is subcooling. म्हणजे saturation temperature पेक्षा temperature at 0.3 is less. So from table, they have given this value HF3 dash किती दिले त्यांनी 49.07. कसं बघायचं हे तर आपण प्रेशर बघायचं 0.3 ला किती प्रेशर आहे 4.93. तिथं आपण काय बघायचं एन्थाल्पी. ठीक आहे सो दॅट इज 49.47 kilojoule per kg and then these values are given to you. okay T3 dash is saturation temperature, so that is 287.45. just here we have calculated, and T3 is given as 9 degrees Celsius, so that we have calculated it as a 282 Kelvin. आता तुम्हाला काय करायचं आहे, we have to calculate H3. H3 will be equal to 49. I will just put these values in these equations. So that will be 49.07 minus आता Cp किती घेणार ह्या केस मध्ये बघा की this is a subcooled liquid, so we have to take C value for liquid. So here the Cp value for liquid is given as 0.963. Okay, so minus 0.963 into delta T will be 287.45 minus 282. Okay, so please calculate this. Oh, great. So Pratik Singh he has calculated. His answer is nearby to others' answer also. So I will take Pratik Mandwale's answer. H3 is equal to, I will take 43.81. So I'm glad that Pratik still remembers how to operate Kelsey. I thought he has forgotten in this lockdown period. So good. Okay. So we'll calculate the COP. COP will be equal to again H1 minus H4 minus divided by H2 minus H1. Now put all these values. H1, how much we have calculated? H1 we have calculated as 175.04. So 175.04 minus H4. So this H3 is equal to H4. Okay. So here we have said that H4, because that is the isenthalpic process, H4 is equal to H3. H3 we have calculated, so that is equal to H4. So minus 43.81 and divided by H2. H2 how much we have calculated? Here I have calculated H2 203.67 minus H1. So that is 175.04. So if you're not able to see this on your screen, I will go to the next slide. So COP will be equal to 175.04 minus 43.81, 203.67 minus 175.04. So calculate the COP. I hope this is what they have asked. So I have one answer, or I have two answers. I have two answers, three answers I have. So I'll take Rohit's answer. So that is 4.58. So that will be COP. Now let us see what they have asked actually. So they have asked to calculate the coefficient of performance and refrigerant effect per kg of working substance circulated. So refrigerant effect is nothing but the heat extracted in the evaporator, so that we are notifying it as a QL. So that is equal to H1 minus H4. Okay, so those who are new, please look at this pH diagrams. So if you take enthalpy difference at 1 and at 4, so that is the heat extracted, that is a QL. So that is nothing but our refrigeration effect. So calculate this. So this will be our this numerator only. 175.04 minus 43.81. This will be equal to 0.32 R. एक 131.23. I think this will be correct. Kilojoule per kg. Okay, so this is your first answer, answer 1. This is your answer 2. Right, so I will quickly recap what we have done in this case. So see, they have given clearly, it is mentioned that vapor is superheated, and they have clearly mentioned it as it is subcooled, or it is cooled to 9 degrees Celsius. So this example was both superheating and subcooling. Now from the given data, I have first drawn the pH and TS diagrams. So those are in front of you. On that diagram, I have clearly mentioned the pressure values and the temperature values. So what will happen automatically, that problem will be reflected on these diagrams. Now they are asked to calculate the COP. Generally, all in this example, they will try to calculate the COP. I have written the formula for COP. Now in this numerical, all values we have to calculate. So in our previous examples, what was there? Either 1 point was on saturated vapor curve, or the 0.3 was on saturated liquid curve. But in this case, each value we have to calculate. Now, H1 value, so they have given it is a 95% dry. So that means I have to calculate by using the dryness fraction. So H1 is calculated. H2 lies on the superheated region. So that is why I have to use the formula, that is the enthalpy at saturated vapor plus Cp delta T. So that way I have calculated H2. Then calculation of H4. So H4 is equal to H3 because it is a constant enthalpy expansion process. 0.3, it lies in the subcooled region. Subcooled enthalpy कशी काढायची? The enthalpy of saturated liquid minus Cp delta T. So that way I have calculated values, and that way I calculated COP. Last was the refrigeration effect. So that is nothing but the heat extracted in the evaporator. That is nothing but H1 minus H4. So that way I have calculated refrigeration effect. Okay, so if they have given the mass flow rate in this case of the refrigerant, I could have multiplied by 8, then I will get the capacity in the terms of kilowatt. ठीक आहे, ह्याला जर मी मास फ्लो रेट न गुणलं तर काय मिळणार मला? किलोवॅट मध्ये आन्सर मिळणार आहे. किलोवॅटला परत मी 3.5 न डिवाइड केलं तर मला काय मिळणार आहे? टन्स मध्ये कॅपॅसिटी मिळणार आहे, टन्स ऑफ रेफ्रिजरेशन. So this is how these examples will be asked. In the assignment, I will give you some examples. You try to solve it. So as we are new to this, you are new to this, it will take time at first. But as you practice, things will be more clear to you. ठीक आहे, समजलं सगळ्यांना? So if you are not understood, you can ask. If you have any doubt, you can ask. This was the end of our numericals in this chapter. And now the remaining theory is what are the factors affecting VCR. Then this chapter will be over. Okay. So I will give you 5 minutes. You can ask your queries. After that, I will start the remaining theory part. So those who have skipped the previous lectures, we have provided the study material sheet. In that you can refer, you can watch the videos. Also, I have shared the PDF files for books. So one book is the RS Kurmi book, and another is the foreign author in that sheet only. Also, I have shared that quiz link in the sheet, so which that quiz we have taken in last week. That link also I have provided under MCQ, so you can go through it. Okay, so I will mail the assignment to you, and then you can solve the example, you can write the theory, you can practice it. So the thing is that this opening of colleges or schools is yet not declared, and whatever happened in your last सेम, तुमच्या 30 सेम मध्ये जे झालं, तुमचे मार्क आम्ही कसे पाठवले युनिव्हर्सिटीला पाठवताना तुमचा अटेंडन्स, तुमचा ओव्हरऑल परफॉर्मन्स आणि तुमचं बिहेवियर हे सगळं कन्सिडर करून आम्ही टर्म वर्क आणि तुमच्या आयसीचे मार्क पाठवलेले. जर वर्स्ट केस मध्ये या सेम मध्ये देखील ते झालं तर तुमची ही आताची जी अटेंडन्स आहे, तुमचे परत ते असाइनमेंट आम्ही जे तुम्हाला देणार आहे ते तुम्ही सबमिट केलेत का नाही, तुमचं ओव्हरऑल बिहेवियर कसं राहिलं ऑनलाईन लेक्चर्स मध्ये, त्याच्यावर आम्ही परत मार्क्स देणार आहे. जर वर्स्ट केस मध्ये असं झालं की परत थर्ड इयर सेकंड सेम सारखी सिच्युएशन आली तर ठीक आहे. सो डोंट टेक लाईटली ऑनलाईन लेक्चर्स, लॉट ऑफ थिंग्स आर इन आवर हँड्स अँड ओके. So today I have attended one webinar. So that link I had shared you on the group. It was related to entrepreneurship opportunities in the cold storages and cold rooms. So that webinar was very good. He gave emphasis on various topics on cold chain, right from harvesting of the crop in the field, म्हणजे शेतात धान्य कापल्यापासून ते कोल्ड स्टोरेज नेपर्यंत लॉजिस्टिक, त्यानंतर कोल्ड स्टोरेजमध्ये गेल्यानंतर होणाऱ्या प्रोसेस, त्यानंतर होणारं फूड प्रोसेसिंग, हे सगळ्या गोष्टी त्यांनी एक्सप्लेन केलेल्या. तर तुमच्यात कुणाला जर इंटरेस्ट असेल एंटरप्रेन्योरशिप इन कोल्ड स्टोरेजेस और रेफ्रिजरेशन प्लांट, dairy plants like that, so we can discuss. So government is offering subsidies in that case. Actually government is promoting the entrepreneurship in cold storages or cold rooms or this cold chain. You can go to the website of APEDA, APEDA, or you can go to this Ministry of Food Processing, or you can go to the, there is a separate body for cold storages, so that is a NCCD, National Cold Storage and some, I think I don't know the full form, but NCCD works for the cold storages only. That also you can check. Okay, I will wait for another 2 minutes, then we can start this theory part. If you have no doubts, then I can start. Okay. So we have just finished the numericals related to VCR cycle. Then we'll now see what is the actual VCR cycle. Okay, so in ideal VCR cycle, so there were two constant pressure processes. There was one isentropic compression and there was one isentropic expansion. But in actual processes, what is different, that we'll see now. So the main deviations from the theoretical cycle and actual cycles are as follows. First one, it is the vapor refrigerant leaving the evaporator is in superheated state. So in ideal, it was dry saturated. In actual, it is superheated. Second, the compression of refrigerant is neither isentropic nor polytropic. Okay. Third is the liquid refrigerant before entering the expansion wall is subcooled in the condenser. So in ideal, that refrigerant is saturated liquid, but in actual it is a subcooled liquid. The pressure drops in the evaporator and condenser. So in ideal, we have assumed that this evaporation and condensation, they occur at constant pressure, but in actual it is different. It is like pressure drops. Okay. तर हे तुम्ही जर HMT मध्ये तुमचं कव्हर नाही झालं नसेल तर तुम्ही कधी हीट एक्सचेंजरचा अभ्यास केला तर त्या केसमध्ये ते फार मोठा क्रायटेरिया आहे. तर पहिला क्रायटेरिया असतो टर्ब्युलन्स, की टर्ब्युलन्स जेवढं जास्त तेवढं हीट एक्सचेंज तुमचं फास्ट होतं. सेकंड इज प्रेशर ड्रॉप. तर असं अजून करतात आयडियली की this heat exchange processes are constant pressure processes, but in actual what happens when the refrigerant or the liquid flows through the tubes or pipes, because of the frictional resistance or and the bends joints, that pressure drops. ठीक आहे, त्यामुळे ते प्रेशर ड्रॉप होतं, तर ते देखील तुम्हाला कॅल्क्युलेशन मध्ये कन्सिडर करावं लागतं. Okay, so if you study this cell and tube heat exchangers or plate heat exchangers, that time you will come to know that we are considering the pressure drop also. इथे प्रेशर ड्रॉप कन्सिडर करून मग आपण पंपची सायझिंग करतो, पंप किंवा कॉम्प्रेसरची सायझिंग करतो. Okay, so I'll quickly draw that diagram. First, I will draw the diagram of ideal VCR cycle. So I'll take the example. I'll take a temperature versus entropy diagram. Okay. So this was your ideal VCR cycle on TS diagram. Now I will draw the actual one. Okay, so I hope that will help. Okay, so first I will start with the entry of evaporator. Okay, so let us say this is our starting point, which is a entry to the evaporator. Now the refrigerant has entered to the evaporator. In that, what happens that heat is being added, okay, at constant temperature. Now heat is being added, it will reach to a point. So that point is saturated vapor point. Let us say that is point 2. So as it said that the end of evaporator or the at the entry of the compressor, that refrigerant is superheated. That means what happens in the evaporator only, the heat is transferred to the refrigerant and it is superheated. So let us say this is superheated. Okay, so it reaches to 0.3 liquid, that the refrigerant is superheated. Now what happens at the entry to the compressor? At the entry to the compressor, there is a certain pressure drop. Okay, so there is a pressure drop 3 to 4. Then when that refrigerant comes in contact with cylinder walls of the compressor, if it is a reciprocating air compressor, sorry, not the air compressor, reciprocating compressor, in that case, when the superheated refrigerant comes in contact with hot walls of the compressor, again there is a rise in the temperature. So this is a fifth point. Now what happened, there is a compression process. So previously it was a isentropic compression, but in actual it is not the case. So this compression will take place like this. So that compression has now finished. Okay. Now at the discharge at constant pressure, there is a drop in temperature. It reaches 2.7. Then at the before the entering the condenser, there is a pressure drop. At the discharge, there is a pressure drop. It reaches to 0.8. Now 8 is the starting of condensation. So it is starting to enter the condenser. So first there will be this cooling. So the superheated vapor is now converted into dry saturated vapor. So let us say there is a 0.9. From 9 at constant pressure, that latent heat will be rejected. It will reach to 0.10. Okay. Then there will be subcooling. Subcooling means cooling below the saturation temperature. So it will come to point 11. Okay. Now this is the end of condenser. 11 is the end of condenser. From 11, it will pass through the expansion wall and it will come to point 1. So this will be expansion in throttling wall. So this is the actual VCR cycle. 1 to 2 and 2 to 3. This 1 to 3 process occurs in evaporator. 3 to 8 occurs in compressor, inlet and outlet, and compressor also. So 8 is the entry to the condenser. 8 to 10, not 8 to 10, 8 to 11 it's in condenser, and 11 to 1 is in expansion wall. So this is the actual VCR cycle. Okay, I will explain again what is happening. So 1 is the entry to the evaporator. It is passing through tubes in the evaporator. It will come to point 2. Point 2 is the saturated vapor. But because of again heat transfer, that dry saturated vapor, it will absorb the heat. It will be converted into saturated vapor at point 3. Point 3 is the inlet. It is just starting to enter the compressor. So while entering, what is happening? There is a pressure drop at the suction side. There is a pressure drop. Then 4 to 5, again temperature rises because it comes in contact with cylinder walls of the compressor. 5 to 6 is the compression, but it is not isentropic, okay, and nor it is polytropic. Again 6 to 7, there is a reduction temperature at constant pressure. 7 to 8, that is a reduction in pressure. Then 8 is the exit to the compressor and entry to the condenser. 8 to 9, the cooling will take place. 9 to 10, and 10 to 11 it is a subcooling. 10 to 11 it is a subcooling. 11 is the exit of the condenser. Okay, then 11 to 1 is a expansion process in expansion wall. So I hope you understood this process of actual VCR cycle. If you have any doubts, you can ask. And draw this diagram, please. So one thing I have mentioned earlier, that was this pressure drop occurs in evaporator and condenser. So that we can show here. So this point 2 will be little bit lower. So in this case, if it is a straight line, okay. So there is a pressure drop in evaporator, so it will reach to point 2 here. Okay. Again, there is a pressure drop in condenser. So if it is a straight line here, okay, so point 10 will be here. So there is a pressure drop in condenser. So it will reach to point 10. Okay, so that lines won't be constant because it is not a isobaric process in actual cycles. There is a pressure drop. Okay. So this is all about actual VCR. Now we'll see what are the factors that are affecting the performance of VCR cycle. So factors affecting the performance of a refrigeration plant. First is evaporation temperature. Okay. Second is condenser temperature. I will explain this one by one in next slides. Third is subcooling of liquid refrigerant. Fourth is superheating of suction gas. Fifth is heat transfer at evaporator condenser. So because of heat transfer at evaporator and condenser, there is a subcooling and a superheating. Presence of non-condensable gases in the system. Yes, so this non-condensable gases, this reduces the efficiency or the COP. Volumetric efficiency of the compressor, multi-stage compression and throttling system. So this multi-stage compression is our next topic. So in second chapter, we'll study what is this multi-stage compression. Design of plant components. So how this load is calculated while designing a dairy plant or a refrigeration plant, that is also important. And last is maintenance of the plant. So how this plant is being maintained, that is also a very, very important thing. So in one lecture I explained you about the evaporator. Evaporator मध्ये काय होत असते जनरली डिफ्रॉस्टिंग होत असते. तर इव्हॅपोरेटर टेम्परेचर कधी कधी ड्यू पॉईंटच्या खाली जातं, त्यामुळे त्याच्या वॉटर पार्टिकल्स जमा होतात आणि त्यातनं काय होतं परत त्यांचं फ्रीजिंग होतं. म्हणजे काय होतंय, इव्हॅपोरेटरच्या कॉइल्सवर एक प्रकारे बर्फ जमा होतोय. ठीक आहे. तर बर्फ जमा झाल्यामुळे काय होतंय, तर त्याचं हीट ट्रान्सफर कोएफिशियंट जो एच आहे किंवा ओव्हरऑल हीट ट्रान्सफर कोएफिशियंट यू तो कमी होतो. तो कमी झाल्यामुळे काय होतंय, तर ते त्याच्यातलं हीट ट्रान्सफर कमी होते. सो इट अफेक्ट्स द ओव्हरऑल परफॉर्मन्स ऑफ द सिस्टीम. आणि कंडेन्सर मध्ये काय होत असते, कंडेन्सर मध्ये ज्या जर वॉटर कूल्ड कंडेन्सर असेल तर वॉटर मधल्या इम्प्युरिटीज जमा होऊन त्याच्यावर एक थर जमा होत असतो ट्यूब्सवर आत किंवा बाहेर, किंवा रस्टिंग देखील होत असतं, त्याच्यावर गंज तयार होतं. सो बिकॉज ऑफ दॅट ऑल्सो हीट ट्रान्सफर रिड्युसेस अँड इट अफेक्ट्स द ओव्हरऑल परफॉर्मन्स ऑफ द सिस्टीम. Okay, so I will show you how these parameters are affecting on the system. So I will draw one pH diagram. So first I will take effect of condenser temperature. So first I will draw one ideal cycle, VCR cycle. So 1, 2, 3, and 4. Now what is happening in this case? We are increasing the, let us say I want to study the effect of pressure, effect of condenser pressure. ह्या केसमध्ये जर मी त्याचं प्रेशर वाढवलं तर काय होणार आहे, 0.3 इथं शिफ्ट होईल कुठेतरी. ठीक आहे. सो दिस विल बी आवर न्यू पॉइंट 0.3 डॅश and it will go here. So 0.2 will be also shifted to 2 dash. Okay. So this is the effect of increasing the condenser pressure. आता ह्या केस मध्ये काय होतं चेक करा, 0.3 डॅश इथं गेल्यामुळं 4 डॅश देखील चेंज होईल, तर तुमचा 4 डॅश इथं येईल. ठीक आहे. सो व्हॉट इज हॅपनिंग इन दिस केस, पहिल्यांदा जर तुम्ही रेफ्रिजरेशन कॅपॅसिटी चेक केली क्यूएल, तर काय होती H1 मायनस H4. ठीक आहे. ती सेकंड केस मध्ये काय झाली, H1 मायनस H4 डॅश, म्हणजे काय झाली या केसमध्ये रिड्यूस झाली. ठीक आहे, रिड्यूस झाली. आणि इथं जर बघितलं तुम्ही वर, तर 2 डॅश पॉईंट इथं आला, त्याची एन्थाल्पी इथं आली, समजा 2 ची एन्थाल्पी इथं आहे, 1 ची एन्थाल्पी इथं आहे. ठीक आहे. तर काय होणार आहे, आधी कॉम्प्रेसर वर्क तुमचं किती होतं, H2 मायनस H1, आता किती झालं तुमचं ते H2 डॅश मायनस H1, तर काय झालं या केसमध्ये वाढलं. So that what happens when we increase the condenser pressure, there is a reduction in refrigeration capacity and increase in compressor work. Second, I will take now evaporator pressure. So same thing goes with the temperature also. If I take the temperature, if I increase the condenser temperature, that time also similar phenomena happens, that the refrigeration effect reduces and compressor work increases. So if I take now evaporator pressure, okay, once again I will draw that ideal cycle. So 1, 2, 3, and 4. So in this case, what I am doing, I am reducing the evaporator pressure. So that will be if I take a lower value. Okay. So I will reach to 0.4 dash. So it will go in this direction. So this will be my 0.1 dash. Okay. So in this case, what is happening? If you see refrigeration capacity, first it was H1 minus H4. Now it is H1 dash minus H4 dash. By looking at the diagram, you can easily say that refrigeration capacity is being reduced. ठीक आहे, त्यामुळे लक्षात ठेवा कधी पण कंडेन्सर प्रेशर कॉमा टेम्परेचर हे कमी असलं पाहिजे आणि इव्हॅपोरेटरचं प्रेशर आणि टेम्परेचर जास्त असलं पाहिजे. जास्त म्हणजे जे त्याचे नॉर्मल रेंज आहे त्यापेक्षा जास्त असलं पाहिजे. ह्याचा दुसरा अर्थ काय, जर मी एसी घरात वापरते, ठीक आहे, माझ्या घरामध्ये एक स्प्लिट एअर कंडिशनिंग आहे, तर त्याचा परफॉर्मन्स कधी जास्त असणार आहे, तर बाहेर त्यावेळेस टेम्परेचर कमी असतं. म्हणजे काय असतं, त्याचं कंडेन्सर प्रेशर टेम्परेचर कमी आहे. असं कधी होतं तर हिवाळ्यामध्ये. हिवाळ्यात काय होतं तर बाहेरचं टेम्परेचर कमी होतं, म्हणजे कंडेन्सरचं टेम्परेचर कमी होतं, म्हणजे त्या केसमध्ये काय होतं, माझा परफॉर्मन्स वाढतो. ठीक आहे. सिमिलरली if I take evaporator, so I'll just quickly draw the diagram so you will understand. Suppose this is a wall. ज्यावेळेस मी एसी घरात लावतो, ठीक आहे, त्याच्यामध्ये काय असते, वॉल माउंटेड मध्ये आत एक पार्ट असतो. आत काय असते, इव्हॅपोरेटर असते आणि थ्रोटलिंग वॉल असते. आउटसाइड जो युनिट असतं इथं, ह्याच्यात काय असते, कॉम्प्रेसर आणि कंडेन्सर असतं बाहेर. ठीक आहे. तर हे झालं आउटडोअर, हे झालं इनडोअर. तर मी काय तुम्हाला म्हटलंय, तर कंडेन्सर प्रेशर आणि टेम्परेचर कमी पाहिजे. म्हणजे काय, ज्यावेळेस विंटर असेल, हिवाळ्यात काय असणार आहे, कंडेन्सर टेम्परेचर कमी असणार आहे, त्या केसमध्ये आपलं परफॉर्मन्स जास्त वाढणार आहे आणि कॉम्प्रेसरला कमी वर्क करावं लागणार आहे. तेच जर इव्हॅपोरेटर टेम्परेचर जास्त असेल, म्हणजे इनडोअरचं जास्त टेम्परेचर जास्त असतं, ठीक आहे, त्या केसमध्ये काय होणार आहे, माझा सीओपी जास्त असणार आहे. म्हणजे आपल्याला काय करायचं थोडक्यात, तर हा गॅप कमी करायचा आहे. हा जो गॅप आहे या दोन्ही मधला, तो गॅप मला कमी करायचा. मला काय करायचं आहे, ह्याचं कंडेन्सरचं प्रेशर टेम्परेचर कमी करायचं आणि इव्हॅपोरेटरचं टेम्परेचर प्रेशर वाढवायचं. म्हणजे काय झालं, हा गॅप कमी झाला. ठीक आहे. ह्याच्या उलट तुम्ही कधी केलं तर, ज्यावेळेस तुम्ही आपल्या थर्मोडायनामिक्स मध्ये रँकिंग सायकल शिकत होता, त्यावेळेस ह्याच्या उलट होतं. ठीक आहे. कारण ते एक हिट इंजिन आहे. हिट इंजिन मध्ये काय असते, तर तुमचं जे वरचं जे टेम्परेचर आहे, बॉयलर प्रेशर आणि टेम्परेचर, ते जास्तीत जास्त पाहिजे. आणि त्या केसमध्ये तुमचा जो कंडेन्सर प्रेशर होता रँकिंग सायकल मध्ये, तो कमीत कमी पाहिजे. म्हणजे काय, तुम्हाला जास्तीत जास्त वर्क आउटपुट मिळते. त्याच्या उलट आपलं कशामध्ये असणार आहे, रेफ्रिजरेशन मध्ये. रेफ्रिजरेशन मध्ये उलट कंडेन्सर म्हणजे जे जिथे आपण हीट रिजेक्ट करतोय ते कमी टेम्परेचरला पाहिजे, आणि जिथून हीट एक्स्ट्रॅक्ट करतोय ते इव्हॅपोरेटर हायर टेम्परेचरला पाहिजे. ठीक आहे. सो दिस इज द सिग्निफिकन्स ऑफ दिस these two terms, condenser pressure temperature and evaporator pressure temperature. Okay, so I will explain what is the effect of this subcooling and superheating. Then we can move towards our last bit. So let me add one more sheet. Okay, so we'll now discuss about what is the effect of subcooling. Pressure versus enthalpy. So if I draw this saturated liquid curve and this is a saturated vapor curve. आता सब कुलिंगच्या आधी मी काय करतो, पहिलं एक साधे VCC सायकल काढून घेतो, VCR सायकल. ठीक आहे. 1 2 3 आणि 4. आता मी काय करतोय, तर सब कुलिंग करतो. सब कुलिंग म्हणजे करतो म्हणजे काय झालं, तर माझं टेम्परेचर सॅच्युरेशन टेम्परेचरच्या कमी येणार आहे. म्हणजे इथं कुठेतरी 0.3 डॅश येईल. ठीक आहे. जर मी ते खाली नेलं तर माझा 4 डॅश देखील चेंज होणार आहे. हा कुठेतरी माझा 4 डॅश येईल. ठीक आहे. तर तुम्ही ह्या केसमध्ये बघितलं, रेफ्रिजरेशन कॅपॅसिटी पहिल्यांदा किती होती, H1 मायनस H4. नवीन ह्याच्यात किती असणार आहे, H1 मायनस H4 डॅश. तर तुम्ही क्लोजली फिगर जर चेक केले तर तुम्हाला कळेल की रेफ्रिजरेशन कॅपॅसिटी वाढली. कॉम्प्रेसर वर्क आहे तेवढंच राहिले. कॉम्प्रेसर वर्क विल रिमेन कॉन्स्टंट. So effect of subcooling is to increase the refrigeration effect. Now if I go for superheating, before compression. Okay, superheating means before compression. First, I will draw that simple VCR cycle. One, two, three, four. Now what I have to do, I have to induce superheated vapor at the start of compression. That means हा point 1 थोडा पुढे जाईल, तर कुठेतरी हा point 1 डॅश येईल. ठीक आहे. आता हा पुढे गेल्या म्हटलं ऑब्विसली काय होणार आहे, 2 देखील पुढे जाणार आहे, 2 डॅश. ठीक आहे. कॉम्प्रेसर वर्क आधी माझं किती होतं, H2 मायनस H1. नवीन ह्याच्यात काय होणार आहे, H2 डॅश आहे मायनस H1 डॅश. आणि नॉर्मली जर तुम्ही मेजर केलं तर ते नेहमी वाढतं. ओके. सो इफ यू आर प्रोव्हाइडिंग सुपरहीटेड वेपर at the start of compression, your compressor work ultimately increases. ठीक आहे. पण तुमचा रेफ्रिजरेशन इफेक्ट वाढतो. ठीक आहे. या केसमध्ये जर तुम्ही रेफ्रिजरेशन इफेक्ट बघितलं तर आधी किती होता, H1 मायनस H4. नवीन ह्याच्यात किती असणार आहे, H1 डॅश मायनस H4. तर हा वाढलाय. ठीक आहे. बट अल्टिमेटली व्हॉट हॅपन्स इन सुपरहीटिंग, the overall effect, so the net effect is too low COP. जरी तुमची रेफ्रिजरेशन कॅपॅसिटी वाढत असली पण तुमचं कॉम्प्रेसर वर्क देखील वाढतंय. म्हणजे रिलेटिव्हली नेट इफेक्ट इज टू लो द COP. तुमची COP कमी होतं. ठीक आहे. So these are the effect of parameters. First we have seen the effect of condenser and evaporator pressure and temperatures. And now we have seen effect of subcooling and superheating. So any questions? So any questions? Okay, so with this our first chapter ends. Okay, Rohit is asking, can we use superheating and subcooling at the same time? Yes, so we have solved one example here. Our last example that involved both processes. It involved superheating, but it was superheating at the end of compression. Okay, but in this case we have used superheating at the entry, so we can use that. So see why superheating is important, because compressors cannot handle liquids. कॉम्प्रेसरला फक्त आणि फक्त गॅसच पाहिजे. त्यासाठी आपल्याला कॉम्प्रेसरच्या इनलेटला वेपर द्यावा लागतो, सुपरहिटेड वेपर. पण त्याच्यामुळे काय होतं, तर तुमचा COP कमी होतो. आता ते जर तुम्हाला काउंटर करायचं असेल तर इथे काय होतंय, इथं बघा तुमचं सुपरहिटिंगमुळे काय होतंय, नेट इफेक्ट इज टू लो द COP. पण ते गरजेचं आहे कारण कॉम्प्रेसरला गॅस पाहिजे. त्याला तुम्ही काउंटर कसं करणार, सब कुलिंग प्रोव्हाइड करणार. सब कुलिंग मध्ये काय होतंय, तुमचं ऑटोमॅटिकली रेफ्रिजरेशन इफेक्ट वाढतो, त्यामुळे त्याचा COP देखील वाढतो ह्या केसमध्ये. ठीक आहे. सो येस, इन ऍक्च्युअल सुपरहिटिंग करावंच लागतंय कारण कॉम्प्रेसरला गॅस लागतो. सब कुलिंग तुम्ही करू शकता जर तुम्हाला रेफ्रिजरेशन इफेक्ट वाढवायचा असेल. ठीक आहे. ठीक आहे. So with this our first chapter ends. So I will just quickly revise whatever we have learned up to this point. So we started with the Carnot cycle, then we saw the reverse Carnot cycle, then we saw the numericals of reverse Carnot cycle. So if I take one example, I will take one example of gate. गेट एक्झाम मध्ये मोस्टली बऱ्यापैकी क्वेश्चन हे रिव्हर्स कॅनॉट सायकल वरच असतात. एखाद दुसरा क्वेश्चन तुम्हाला कुठे ह्याच्यावर दिसेल, VCR सायकलवर. ठीक आहे. देन वी सॉ बेल कोलेमन सायकल. बेल कोलेमन सायकलचे आपण न्यूमरिकल्स डेरिवेशन सॉल्व्ह केले. So one big application of Bell Coleman cycle, that is the air refrigeration system. ते देखील आपण बघितलं कशामध्ये, एअरक्राफ्ट मध्ये. तर एअरक्राफ्ट मध्ये कशा प्रकारचे रेफ्रिजरेशन सिस्टीम यूज केली जाते ते देखील आपण पाहिलं. ठीक आहे. तर इफ यू रिमेंबर, एअरक्राफ्ट मध्ये काय असतं, तर आपल्याला आत प्रेशर आणि टेम्परेचर 1 बार ठेवायचं असते, 300 केल्विन ठेवायचं असते. पण ज्यावेळेस तुम्ही हाय अल्टिट्यूडला जाता त्यावेळेस काय होत असतंय की तिथं प्रेशर फार कमी असतं, 0.2 बार असतं आणि टेम्परेचर -40 डिग्री सेल्सिअस असतं. त्यामुळे आपल्याला तिथे देखील एक चांगली रेफ्रिजरेशन सिस्टीम द्यावी लागते. देन वी मूव टुवर्ड्स द VCR cycle, vapor compression refrigeration cycle, and then we solve this numericals related to it. Last, in this lecture, we have studied what are the factors affecting the performance of VCR cycle. That is the condenser, evaporator, pressure, temperature, subcooling, and superheating. So in assignments, I will give you more examples. So it is expected that you will solve and submit the assignment. Once again, I will repeat. So the condition when these colleges will be open, it is yet unknown. So what we did in your third year's second sem, similar approach may be followed. So your attendance and all these things, assignment and your behavior, that will be counted. Okay. So as a bonus, I will tell you one practical example. So that your confidence will be more. तुम्हाला असं वाटणार नाही की हे सगळं थेरॉटिकल चालू आहे. एक प्रॅक्टिकल एक्झाम्पल मी तुम्हाला देतो. सो इफ यू वॉन्ट टू डेअरी कुलिंग प्लांट, डेअरी चिलिंग प्लांट पण त्याला म्हणतात. ठीक आहे. तर ते कसं करायचं. ठीक आहे. So design of a dairy cooling plant. So simple way for estimating the capacity of refrigeration plant of a bulk cooler. तर त्याला bulk cooler देखील म्हणतात. Having 5000 liters milk storage capacity is given below. Given below म्हणजे I will explain. Density of milk. तर दुधाची डेन्सिटी किती असते. So it is as good as 1032 kg per meter cube. Specific heat of milk, it is 3.9 kilojoule per kg Kelvin. Initial temperature of milk, सर हे जनरल त्यांनी टेम्परेचर घेतलंय 35 डिग्री सेल्सिअस. फायनल कुलिंग टेम्परेचर म्हणजे ज्यावेळेस आपल्याला मिल्क स्टोअर करायचं असते जेणेकरून ते खराब होऊ नये. ठीक आहे. तर काय असतं, दुधामध्ये बरेचसे मायक्रो ऑर्गॅनिझम असतात, फंगी असतात, त्याच्यामुळे काय होतं, दूध खराब होऊ शकतं, दूध फुटतं, म्हणजे दूध काय म्हणतात एजिंग प्रोसेस स्टार्ट होऊ शकते. आपल्याला ते जर रेस्ट्रिक्ट करायचं असेल तर आपल्याला ते लो टेम्परेचरला स्टोअर करावं लागेल. तर दुधासाठी टेम्परेचर आहे 2 डिग्री सेल्सिअस. तर ह्यात आपल्याला करायचं की ऍज अ रेफ्रिजरेशन इंजिनियर आपल्याला सांगायचं की किती कॅपॅसिटीची सिस्टीम लागेल ह्या सगळ्या प्रोसेससाठी. आणि अजून एक गोष्ट, ज्यावेळेस दूध थंड करत असतात तर ते आता इथं 5000 लिटर्स दिलंय, तर ह्याला सहसा लागते 4 तास तर लागतात. असं नाही की आपण कूल करायला ठेवलं आणि लगेच 10 मिनिटात कूल झालंय, असं नसतं. त्याला एक स्लोली स्लोली कूल करत 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 ते 2 डिग्री सेल्सिअसला घेऊन जातात. ठीक आहे. सो दिस इज द ऍक्च्युअल प्रोसेस. सो कॅन यू कॅल्क्युलेट इन दिस. सो I will give some 5 minutes. You read the problem. If you can solve, if you get the idea, you share with us, then we can calculate. So any idea how we can solve this? Yes, so I'm asking you, what should be the approach while calculating the capacity of this refrigeration plant for a dairy cooling purpose? Yes, any answers? So the values are in front of you, so you have to just calculate what it will be capacity, okay, of the refrigeration plant. So shall I take names? Mahesh Shinde, are you there? Mahesh Shinde. Sonali Chavan, any idea? What we have? Yogesh Pandit. So I'm just asking your ideas, like how we can solve this example. So let it be wrong, but at least I should. What I'm expecting you that you should apply your knowledge of refrigeration while calculating the capacity of this dairy cooling plant. Okay, I'll solve it, but I seriously expected some answers, not the final answers. Like I expected some approach. It is a straight away example. What they have given is they have given the mass is given. I will take like volume. Okay, that is given as 5,000 liters. Okay, then they have given the density. It's given as 1.032 gram per centimeter cube. That is nothing but sorry, not 1.1032 10 to power minus 3 into 10 to 3. Yeah, this will be it. Kilogram per meter cube. Then specific heat of milk, it is given as Cp. C is given in this case, it is 3.9 kilojoule per kg Kelvin. Okay. Initial temperature T out, let it be 35 degrees Celsius. So this will be. So yes, Rohit, that is what I expected. It is very simple calculation actually. We have to calculate how much heat we have to remove. Then we can calculate per hour, then in kilowatt. Okay, that is the correct approach. And T, so let us say T out and T in is 2 degrees Celsius. So that will be 275 Kelvin. This will be 308 Kelvin. Okay. So our task is to calculate refrigeration capacity QL. So that we can calculate like MCP, MC delta T. How to calculate mass? Mass we can calculate from density into volume. So here it will be 5000 into 1032. Okay. So don't take 1.032 because it is in gram per centimeter cube. If you want to convert gram per centimeter cube, so that you have to multiply by 1000. Okay. Into CP is given 3.9 and delta T is here it is 308 minus 275. Okay, sorry, this is a 5000 liters. So if I want to convert it into meter cube, that will be 5 meter cube. Yes, Pranil, thank you for that. So this will be 5. So if you want to convert liters into meter cube, you have to just divide by 1000. So this will be 5 into density into its specific heat, which is in kilojoule into delta T. So please calculate this. So this value will be again kilojoule. So tell me the answers for this. Okay, Rohit, I think that value is very large. Is it correct? Pranil, what is the answer? So Pranil, can you calculate or is it correct? Calculate this value for QL. Then from this we can calculate the capacity if you take like for 4 hours. So shall I calculate or let's calculate and tell me the answer. So 664.92 kilojoule. Okay. So this process is to be carried out it is in 4 hours. Okay. So what will be the QL dot? So this will be divided by 4 hours. So 664.92 divided by 4 into let us say 3600. So I have to convert hours into seconds. So this will give me the answer in kilowatt. So what will the this flow rate? We calculate how much heat has to be removed. Then I said that this process, whole cooling process, has to be carried out in 4 hours. So what I have done, I have divided by 4 hours. These hours I have converted into seconds. So what will be its value? Anybody calculated? So 46.11 as Rohit has calculated. So that will be in kilowatt. If I want to convert it in tons, so I have to divide it by how much? Please tell me the value in tons of refrigeration. So tell me the answer in tons. Yes, so what I have to do, I have to divide it by 3.5. So if I divide 46.11 by 3.5, I will get a value. So I'll take Anna Sirsat's answer. So that is 13.17. So Anna is my project student, very intelligent student. 13.17 tons will be the capacity. Okay, so ह्याचा सार काय सगळ्याचा तर माझ्याकडे 5,000 लिटर दररोजचं एक समजा दूध येत असेल किंवा 4 तासात मला 5,000 लिटर थंड करायचं असेल. थंड कसं करायचं मला 35 डिग्रीवरून 2 डिग्रीला थंड करायचं आहे. तर त्यासाठी मला किती कॅपॅसिटीचा रेफ्रिजरेशन प्लांट लागेल. तर ते आपण थोडक्यात कॅल्क्युलेट केलं. सो दॅट कॅपॅसिटी 13.17 ही काढली मी कॅपॅसिटी. आता इथून पुढं माझं काम काय असणार आहे, सिलेक्शन करणे. ह्या कॅपॅसिटीला मला मल्टी स्टेज कॉम्प्रेशन करायचं असेल तर किती कॉम्प्रेसर लागतील. त्यानंतर कंडेन्सर इव्हॅपोरेटर मला सिलेक्ट करावं लागेल, थ्रोटलिंग वॉल, परत बाकीचे जे इन्स्ट्रुमेंट आहेत ते मला सिलेक्ट करावं लागतील. त्यांचं मला काय करावं लागेल, असेंब्ली करावं लागेल. ठीक आहे, ते असेंब्ली केल्यानंतर मग काय करावं लागेल, टेस्टिंग करावं लागेल. टेस्टिंग केल्यानंतर मग प्लांट वर्किंग मध्ये मी आणू शकतो. देन देर विल बी अ मेंटेनन्स, रेग्युलर मेंटेनन्स दॅट विल बी कॅरीड आउट. पहिली स्टेप काय असते, कधी पण कॅल्क्युलेट द लोड. तुमचा जो हीट लोड आहे तो कॅल्क्युलेट करायचा. त्यानंतर सिस्टीम डिझाईन करायची, सिस्टीम प्रोक्युरमेंट करायची. ठीक आहे, प्रोक्युरमेंट झाल्यानंतर ऑपरेशन्स आलं, ऑपरेशन्स मध्ये मग मेंटेनन्स आलं. हे सगळं तुम्ही करू शकता. ओके, so that was a bonus example for you. So those who are interested in GATE exam, they can search for these examples from the Made Easy website, or there are other websites also. So one of this I will just show you quickly. I think it is gone somewhere. Oh, okay. So I have Googled it on related to refrigeration rack related examples. So you can Google, or you can go for Made Easy books. There you will easily find these examples. So examples are there. This are related to second section. Just so one example is there. Uh, if you want to solve, you can solve. It is asked in GATE 2016 for 2 marks. So such examples you will see in those books. Okay. So GATE exam is now for third year students also can give, not only for final year students. And it is the date is also extended. So those who are preparing for GATE, they should start as early as possible. At least to keep your notes ready. तुमचे नोट्स रेडी असतील त्यानंतर तुम्ही इझिली प्रॅक्टिस करू शकता. प्रॅक्टिस जेवढं जास्त कराल त्यानंतर तुम्ही मॉक टेस्ट असतात, मॉक टेस्ट सॉल्व्ह करा. जेवढी तुमची जास्त प्रॅक्टिस होईल तेवढं तुमचा स्वतःवरचा कॉन्फिडन्स वाढेल. एकदा स्वतःवर कॉन्फिडन्स आल्यावर मग काय काय म्हणजे दुनियात तुम्हाला कोण काय जरी म्हटलं तर तुम्हाला फरक पडत नाही. ठीक आहे. Okay, so quickly I will take the attendance and then we can stop. So just bear with me for some minutes. Okay. So I have taken your attendance. Thank you for attending. I will soon give you the assignment, and from Monday we can start our next chapter. So thank you for being here.